Hi, welcome back to Unit 13, Electromagnetic Induction. This is topic 13.4. So now we're going to talk about inductance. So now we're going to move into another type of or two more types of circuits after this in 13.5 and 13.6. So inductance is the tendency of a conductor to oppose a change in electrical current. So there's a couple things that it depends on. So it depends on the physical properties of a conductor. And an inductor such as a solenoid is a circuit element that has significant inductance. And so inductance is L, right? Let me do it this way. So inductance is L measured in henries, okay, or H. And so the induction of a solenoid, is L sub sol is the mu. So again, this permittivity or permeability, N squared A over L. Okay, so N is the number of turns, A is the area, L is the length of the solenoid. Because what happens is a solenoid is a coil of wire, right? That is going to be of length L, right? The area is going to be this cross-sectional area, and then the number of turns. Okay, it could be a 1 turn, 30 turn, 900 turn. And N over L, we talked about this a couple, I think in Unit 12, N over L is what's called turn density, so number of turns per unit length. Okay, and what happens is inductors are going to store energy that is created by the current inside that inductor. And so the energy stored is going to be 1/2 Li squared. Again, L is the inductance of the inductor. I is the amount of current. So the energy stored in the magnetic field generated by an inductor is dissipated through a resistor or used to charge a capacitor. Because what we're going to do is we're going to have RL circuits, or resistor inductor circuits, and then we're going to have RC circuits, which are not RC, sorry, we've already talked about those, but LC or CL circuits, which are inductor capacitor circuits. And so what happens is transfer energy generated in an inductor is going to change to other forms of energy. And again, we always obey our conservation laws. And by applying Faraday's law to an inductor and using the definition of inductance, induced EMF can be related to inductance and the rate of change of current. So what happens is this is called self-inductance. So the induced EMF is going to be, is going to be negative inductance times di dt. Okay, and this is known as self-inductance. And as you can see here, the big use of inductors in the world are transformers for electrical power. Okay, so let's look at an inductance example. So we have an inductor with an inductance of 0.30 henries connected in series with a resistor, and both are connected to a power supply as shown. The power generates a current I that is given as a function of time t by the equation of I equals I0 1 minus t over k, where I0 is 4, k is 2. What is the magnitude of the potential difference across the inductor induced by a changing current? So we know it's going to be E, right, or EMF, or epsilon, L di dt. And we don't have to worry about the negative sign because it tells us what is the magnitude. But we need to figure out di dt. And so we're going to do dt of I0 1 minus t over k. All right. And I mean, you could do some simplifying here. Okay. But, you know, if we plug in what t and k are, because they tell us, well, there's I0 and k. So we can just say it's going to be ddt of 4 times 1 minus t over 2, because they tell us k is 2. Right, and I can, again, keep doing some algebra and simplifying this. And if this is your first adventure into calculus, right, I would rewrite as much as possible. So we know our current equation is 4 minus 2t. If we take the derivative of that, that's going to tell us that the change in our di dt, right, is just simply going to be 2, right? Or in this case, negative 2, but we're not worried about, excuse me, the magnitude, or we're not worried about the direction. We're just going to worry about the magnitude. So all we do now is go back. We know we have a 0.30 Henry inductor. We know our di dt is 2. So the induced EMF is going to be 0.60 volts. Okay. Now in this section, you could see that the self-induced EMF by the inductor, right? That's what the other equation is. This is our self-induced EMF. This is a very, kind of, if you want to say, simple version of this. Now, when you start really focusing on that, what happens when you have the resistor in there? What happens when you have a capacitor in there? Now you start getting into more involved questions, and that's going to be the next 2 topics.